Shalom! It is time for the final episode in this 3-part series about learning to utilize parallel resources in C++ programming. In the first episode we learned how to extract the best performance from a single CPU core. In the second episode we learned to utilize all cores within the CPU. But what would be even more efficient than utilizing a processor to the maximum? Well, of course, utilizing more than one processor. So how exactly would we go about doing that? How about using multiple identical processors? This is no different than using multiple CPU cores, and we already covered that in episode 2, so scratch that off the list. How about using multiple computers? This is called cluster computing or clustering. Clustering is usually, but not always, done on operating system level with tools such as NVidia. The same program is started on multiple computers with data collected in one place. It usually does not require any changes into the program source code, and that kind of thing is not what I had in my mind. That leaves option 3, using multiple different processors. Within modern PC hardware there is often found a very powerful coprocessor. This coprocessor is the graphics processing unit, or GPU for short. The GPU is capable of general-purpose computation, much like the CPU, but with advantages and disadvantages. Unlike the CPU, which can run maybe 4 or 16 threads, the GPU can have hundreds or even thousands. According to the Steam Hardware and Software Survey of May 2017, the most popular gaming graphics card is currently the NVIDIA GTX 750 Ti. It has 640 CUDA cores. The GTX 1080 Ti, released just a couple of months ago, has 3584 CUDA cores. And guess what? The GNU compiler collection supports it. Computing on a device is called offloading. Right now GCC supports offloading to 3 different platforms: NVIDIA PTX-enabled graphics cards, Heterogeneous System Architecture, or HSA for short, which right now is only used to offload code for AMD graphics cards, and Intel Many Integrated Core Architecture, or MIC for short, which is mainly used for running code on Intel Xeon Phi coprocessors, which are based on the x86 architecture but are capable of running 256 concurrent threads or more. Sadly, I don't have one. They are quite expensive. Offloading works like this. You write a single program. Within that program some parts will be compiled to run on the host computer and some parts will be compiled to run on the device. Some parts may be compiled for both. The same goes for constant data and also for variables. The device and the host computer might not share RAM, which means that all arrays and other data must be passed back and forth between these units. Offloading in GCC is done using one of the following 2 standard extensions: OpenMP and OpenACC. These features are not usually enabled in your Linux distribution. You can enable them by building GCC from source code. Instructions can be found on the GCC website. Let's study OpenMP first. Our baseline program is the vanilla single-threaded non-simmed Mandelbrot fractal renderer that I introduced in episode 1. The plan is to have the heavy stuff, fractal calculation, all happen on the external device. So iterate is declared as target code. Anything declared between these 2 programmers will be compiled for the target device, not for the host. Then some reorganization to put all the code that will be run on the target device in one place and the host device code in another place. Separate those 2 parts. The offloading itself happens with a single pragma, just like was the case for the parallelization in episode 2. Finally we take the resulting iteration counts for each pixel using a STL library call and convert the iteration counts into colors locally, which is a quick operation. Let's review the components of the OpenMP pragma. The word target means that the next statement will be run on the device rather than on the host. The word teams means that on the device a league of teams will be created. This means that instead of a single team of threads, there will be multiple groups, or gangs, or blocks, or teams, whatever you want to call them, and each of them contain multiple threads. Distribute parallel for means that the following for loop will be divided among these threads, so that each iteration will be run exactly once in unspecified order, but multiple iterations may run concurrently. Collapse 2 tells OpenMP that the following two for loops should be treated as one unit. All combinations of the iterations of the two loops should be distributed across threads. Without the collapse keyword, only the outer for loop would be distributed and the inner for loop would be run consecutively by each thread. The map keyword controls the relationship between host memory and the device memory. Specifically, we send these variables to the device, and once the device has done calculating, we receive the result array from the device. When you run the program that uses OpenMP offloading, you use the OpenMP default device environment variable to choose which device to run on. In my case, I want it to run on the NVidia GTX 970, so I select OMP default device is 1. And the results are... Huh? What? I don't understand. Why is it so slow? It is definitely running on the GTX 970 according to NVIDIA settings. Okay, now it crashed. Let's move ahead, maybe there will be an explanation later. OpenACC. OpenACC is a different standard by different people that does pretty much the same as OpenMP, except its focus is totally on offloading, whereas OpenMP began from making native parallelism easy. Translating OpenMP offloading programmers into OpenACC programmers can be easy or it can be difficult. At easiest, it is just a change of terminology. What OpenMP calls a team, OpenACC calls a gang, and so on. OpenACC defines a very elaborate memory model involving allocations. It would take me at least half an hour to describe how it all works, but in this example I am just copying data in and copying data out. Done. Let's check out the performance. It's faster than the OpenMPC offloading version, but still much slower than the vanilla offloading version. And it crashed too. Apparently I hit a watchdog timeout. It turns out that the NVIDIA driver kills the task if the function takes longer than 7 seconds to execute. Now it is quite surprising that the GPU accelerated program is slower than the native program, but there may be an explanation. The graphics cards may have hundreds or thousands of threads, but what they actually have is functionally closer to simmed than to threads. The GPU acceleration works best with programs where the exact same calculation is performed to a large set of data. Unlike CPU simmed, GPU acceleration can cope with situations where the calculations diverge into different branches using if-elses, but the performance will suffer greatly whenever that happens. To give GPU acceleration the final benefit of doubt, I went ahead and translated the program into CUDA. This means that instead of GCC, we will use NVIDIA's NVCC to compile the program. CUDA is actually just a fancy name for plain old C++ with some extensions. You heard it. CUDA is C++. If you can write C++, you can write CUDA. Now the extensions that make CUDA useful are the following. Each variable declaration can be prefixed with one of the following optional attributes: constant, device, or shared. The differences between these attributes lie within the access permissions and lifetime. Each function declaration can be prefixed with one of the following optional attributes: device, host, device and host, and global. The entry point between the host code and GPU code is called a kernel, and it is indicated by the global keyword. Kernels are invoked using a special syntax that resembles the C++ template parameters. The two parameters within these special brackets are the number of blocks and the number of threads per block. Each of these parameters is actually a three-dimensional entity, but I usually treat them as scalars. Within the kernel, the compiler automatically defines a set of variables that can be read. Block dim, which is the same as the block dimension that was passed in the special bracket parameters. Block IDX is the block index that is currently being executed. It runs from 0 to the block dimension. Thread IDX is the thread index that is currently being executed. It runs from 0 to the maximum number of threads that was passed in the special bracket parameters. Warp size is an architecture-dependent number of threads per warp. The warp is equivalent to a simmed unit size. Imagine each of these Chinese letters is a single thread. A single block can include a number of threads, but all threads belonging to a single warp always execute exactly the same code for different data. If your simmed code contains branches, the GPU will temporarily stop all the other threads in the same warp, because threads belonging to one warp can only execute one sequence of code. Essentially, the performance would diminish by a factor equivalent to the warp size. The good news is that unlike in CPU simmed, the GPU driver can actually migrate threads between warps to utilize them more efficiently. But this is only a best effort process, and how exactly it works is neither disclosed nor set in stone. CUDA also defines some vector data types. These are vector data types in name only. CUDA hardware contains no simmed instructions because the hardware itself is a simmed machine. According to my tests, there is no performance benefit to using these. Also, CUDA contains a huge library of functions both for the host and the device. And by huge, I mean it is massive. There are like 150,000 lines of physical code in the header files alone. That number is within the same ballpark as the amount of code in a recent Linux kernel, and that was just header files. You could spend a year just learning how to use all these libraries. When converting the Mandelbrot fractal renderer into a CUDA program, the first order business is to convert the iterate function into a kernel. This is done by adding the global attribute. Now, because this function will be called thousands of times with identical parameters, with only the block and thread indexes differentiating the different calls, we will need a couple of more data items to make the parameters useful. Namely, the center coordinate in the fractal, the zoom scales, and a pointer where all the results will be stored. To invoke the kernel, we will of course use the bracket syntax introduced at 9:46 in this video. The number of blocks times the number of threads must be at least as big as the results array. I set the number of threads arbitrarily as 128, and the number of blocks is calculated from the need. Now the GPU code cannot write directly into the host computer's memory, so we will need to allocate memory directly from the graphics card. The CUDA-malloc function allocates GPU memory. This memory pointer will be passed to the kernel, and the CUDA-memcopy function invoked here will copy the data from the GPU memory into the host memory once the GPU code has done executing. Here we go! Finally it's faster than anything else so far. It dances a little with the OpenMP thread version, but then shakes it off with a huge margin. In the end, this is 17 times faster than the vanilla version and 2.5 times faster than the thread loop. Can I make it faster? Well, first of all, I think the transfer between the GPU and host memory may be a bottleneck. I should at least try and see what happens if I reduce the array of 32-bit floats into an array of 16-bit ints. I should also try multiple streams. CUDA operates using a stream of operations. A stream is like a pipe from which the graphics card driver pulls tasks that it processes in a sequence. Right now my stream looks like this. Calculation, transfer, calculation, transfer. Each period of calculation is followed by a period of memory transfer. During the memory transfer, the CUDA cores are actually idle waiting for work. But it is actually possible to have more than one stream in CUDA. If I start another task in the second stream when the first stream is transferring data and vice versa, the GPU would be performing calculation tasks back to back with absolutely no idle time. It would mean perfect 100% utilization of the GPU. Let's try that! So, 2 streams. To support the 2 streams we need all kinds of bookkeeping. There is a counter for the next stream to be occupied, the number of streams currently processing data, and flags indicating the same. They are created with a CUDA stream create function. The memory buffers must also be duplicated. The memory copying will now happen with a CUDA memcopy async, meaning that it will proceed asynchronously. All of the remaining changes to the main program are just gymnastics around the asynchronous relationships between the calculations and the processing of the results. The main loop now begins with interpreting the results, that is, converting the array of iteration counts into pixels, rendering the pixels, and updating the inaptly named boolean variable need moment that controls whether periodicity checking will be enabled for the next frame. Before we can assume that the results are available, the CUDA stream synchronized function must be called. It waits until all commands in the specified stream are completed. The result is a very slight performance improvement, and by very slight I mean it's almost no improvement at all. In the end it's like a single % faster than the first CUDA version, totally negligible. As expected, the margin to the CPU versions is greatest when the majority of the iteration loops iterate for a long time. Any time that different iteration loops branch at significantly different moments, such as in the very beginning at the outermost zoom level, the CUDA engine performance suffers for reasons that were explained at 10:57 in this video. Finally, I made a version that combines all best techniques from all 3 episodes. First, there are the 2 CUDA streams. In addition, there are 8 native C++ threads, each of them calculating the image using simmed acceleration. In total, there are 10 processing units, each of them responsible for a single picture. Because of this, different frames take wildly different times to calculate. The following chart is actually a smoothed data where the elephant-sized variations between the render times of different frames are somewhat evened out. In the end it is about 40 times faster than the vanilla version. Now I know what some of you are thinking. I know because I thought the same. Isn't there overhead in calculating multiple frames in parallel? Would it not be better for cache efficiency to work on a single frame using multiple threads? Cache efficiency notwithstanding, it is actually faster to calculate multiple frames in parallel, as you can see from this chart. The reason is that when you process a single frame using threads, say by assigning each scan line to the next available thread, there is a situation when the frame is almost complete, where some threads are idle but some are still working. The next frame cannot be started before all threads are finished. And this moment when some threads are idle just does not exist when you process multiple frames in parallel. Now you might think, how about if we start assigning threads to the next frame when they become free, while some threads are still calculating the previous frame, instead of waiting until the previous frame is complete? I thought that too. In fact, the chart you see on the screen is the result of that thought process carried to its end. The one that I described earlier was even slower. Oh, this screen again. Does this mean I should say some words like conclusion or something? Ah yeah, I know I pulled some lines straight and made some inaccurate generalizations here. For instance, CUDA is not actually C++. NVIDIA's NVCC is actually based on LLVM and is capable of adding the tiny CUDA extensions to many different languages like Fortran for instance. Essentially the same principle how OpenMP works, but still different some way. The purpose of this video series was to give you some ideas and inspiration to help you look where you didn't know to look before. There are other people who make comprehensive references and tutorials. In any case, please do check the video description and the links therein for all the information that I could not pack into the video itself, and check out the comments on the video as well. I will also gladly reply to all polite comments, although I do hope you do your research first in case it's a frequently asked question. Thank you for all your support. Thanks to people who translate captions to different languages. Huge thanks to all 35,000 or more people who have hit the subscribe button. You are awesome. I wish everyone was like you. Thanks to people who give me awesome ideas for future videos and live streams by asking fascinating questions in the comments. I hope you all have a fantastic day. See you again.